Hello everyone. So far we have seen what is a signal, what is a system, and also different types of signals. Okay. The next topic is mathematical description of a continuous time signal. That is, whenever you have certain signal, how do you describe it mathematically? So this mathematical description is useful for analysis of systems. Let us say I have some system and I want to find what is the response of the system for a particular input. So once you have the mathematical description of the input, we can determine the output or what is the response of the system. Okay. So the mathematical description of a continuous time signal is useful when performing analysis of signals and systems. Analysis of signals and systems. Okay. Now, such a mathematical description of a continuous time signal is known as function. Okay. I am representing a signal as a function. That is how this signal is changing with respect to some independent variable like time. Okay. So if I take some signal g which is changing with respect to time, then g of t is known as the function of the given signal. So the mathematical description of a signal is known as function. Okay. So the function is nothing but mathematical description. Mathematical description of a signal. Okay. So now, because function is simply the mathematical description of a signal, I can make use of the term signal or the term function interchangeably. That is, if I say a signal, if I use the term signal or if I use the term function, both mean the same. So I can make use of these two interchangeably. Okay. Interchangeably. Now, the most frequently used signals or functions used for analysis of signals and systems are the exponentials and sinusoidal signals. Okay. So the most frequently used functions for analysis of signals and systems are exponentials and sinusoids. So these are the most frequently used functions. Now, since you are representing a signal or continuous time signal as a function, you call this continuous time signal also as continuous time function. So continuous time signal is also referred to as continuous time function. Okay, we also call it as a continuous time function. So what is a continuous time function? So we have already seen under the different types of signals, we have continuous time, discrete time, and digital signals. So continuous time signal is the one where the signal is having value at every instant of time. So similarly here, continuous time function is the function where the function is having value at every instant of time. Okay. So that is what is a continuous time function. So we'll see some examples for continuous time functions. Let us say I have I have a signal or a function g of t. So g is a function, okay, which is varying with respect to time. So I have some function which is varying in this manner. Okay, this is my continuous time function. So why do we call it as continuous time function? This function is having value at every instant of time. So at whatever instant you are taking, the signal is having certain value or the function is having certain value. So this is some example for a function. Okay. Now, so here, as I have told you, the signal can be represented as a function, that is called as the mathematical description of a signal, but not all signals can be represented as functions. Okay, so we are representing the signals as functions to the extent possible. To the extent possible, that is, we cannot represent all the signals as a function. Some signals may be varying with respect to time in such a way that I cannot write the mathematical expression or I cannot write the function for that particular signal. Okay, but to the extent possible, okay, to that is, we can try writing the mathematical expression or functions to the signals as far as possible. Okay, that is what is meant by to the extent possible. Now, this is one example for a continuous time function. Now, we will give one more example for a continuous time function. Let us denote this also with g of t. So, this is also a continuous time function. Okay, this is a continuous time function which is changing with respect to time continuously. Now, there may be some functions which are changing suddenly. That is, let us say this is my starting time. So there is a sudden increase in the amplitude at 0 seconds. Then it will remain constant for a few seconds. Then it is suddenly falling down. Then it is once again suddenly increasing. And it is suddenly decreasing here, and so on. So what is happening here? The signal is changing suddenly at some instance of time, which are known as the discontinuities. You can see there is a discontinuity here. The signal amplitude is suddenly falling down. So here there is a discontinuity. The signal amplitude is once again falling down. There is a discontinuity here. That signal amplitude is suddenly increasing. So on. So all these points are the points where the signal is changing suddenly, or these are also known as discontinuities. These points are known as discontinuities. Okay, so such a signal which is having discontinuities is called as a discontinuous signal. So this is a discontinuous signal, whereas these are not discontinuous signals because the amplitude is changing slowly. Okay, there is a smooth change in the amplitude. It is not suddenly increasing or suddenly decreasing, but here there is a sudden increase or sudden decrease in the amplitude of the signal. So such a signal you call it as a discontinuous signal. So this signal, whatever I have drawn, is a discontinuous signal. Discontinuous signal. Okay. So unlike these two, this is a discontinuous signal. Now, one thing which is important here is you should not get confused with the discrete time and discontinuous. So discrete time is the signal where the signal is having value only at discrete instance of time, whereas the discontinuous signal is one which is continuous in time but there are some discontinuities. That is, at some instance of time, the signal is suddenly changing within zero time. The amplitude is falling down or the amplitude is increasing. Okay, such a signal is known as a discontinuous signal. So first, discontinuous signals. For example, this is my this instant of time is t naught. Let us say this is the instant of time. T is equal to t naught at this time. So before t is equal to t naught, if I represent the signal as g of t naught plus epsilon, that is, t naught minus epsilon, that is just before t naught. And if I represent the signal after t naught as g of t naught plus epsilon, that is, after t naught, that is t naught plus epsilon, that is epsilon time after t naught, epsilon before t naught. So this is my g of t naught minus epsilon, this is my g of t naught plus epsilon. Then what we can write is limit epsilon tending to 0, g of t naught minus epsilon is not equal to limit epsilon tending to 0, g of t naught plus epsilon. Okay. So let us see why these two are not equal. Let us say I am starting from g of t minus epsilon, t naught minus epsilon, and I am making epsilon tending towards 0. Then if epsilon is tending to 0, this t naught minus epsilon approaches this point. Okay, this is the amplitude of the signal at when epsilon is tending towards 0. Okay, it slowly moves in this direction. Okay, in this direction it approaches this value. Now when epsilon is tending towards 0, the time is decreasing here. So this amplitude is slowly moving in this direction and finally it reaches this value. Now these two values, which is limit epsilon tending to 0, g of t naught minus epsilon, and this is the amplitude with epsilon tending towards 0 of g of t naught plus epsilon. So these two amplitudes are not same, these two are not equal. Okay. So this is what is a mathematical description of a continuous time signal. Now we have seen what is mathematical description of a continuous time signal, which is known as the function. Okay, so that is why we use signal and function interchangeably. Okay, now we'll see the most frequently used continuous time functions which are used for analysis of signals and systems. So they are sinusoids and complex exponential functions. Okay, so let us see what is a sinusoidal function. So if I represent my sinusoidal signal as a function, which is known as sinusoidal function, if I represent it as g of t, which is equal to a cos 2 pi t by t naught plus theta, which is also equal to a cos 2 pi f naught t plus theta, that is 1 by t naught is the time period, 1 by t naught is the frequency, so f naught. And 2 by f naught is actually representing the angular frequency or radian frequency, which is a cos omega naught plus omega naught t plus theta. Theta is the phase angle. So this is the function for sinusoidal signal, or it is the sinusoidal function. So what is the second important function used for analysis? That is exponential function or complex exponential function. Complex exponential function. Okay. So what is complex exponential function? So g of t is equal to a into e power sigma naught plus j omega naught into t, which is equal to a into e power sigma naught t. Okay, if I split this exponential, e power sigma naught t into e power j omega naught t, e power j omega naught t can be written as cos omega naught t plus j sin omega naught t. So cos omega naught t plus j sin omega naught t. Okay, so these are the functions for sinusoidal signal and complex exponential signal. Okay, Let us see what are the different parameters. If I take sinusoidal function, capital A represents the amplitude. So what is the amplitude of the function? Okay, that amplitude depends upon what signal it is. If it is a current signal, the amplitude unit will be microamperes. If it is a voltage signal, the amplitude unit may be volts and so on. Okay. Now the T naught is the time period because it is a sinusoidal function. The sinusoidal function is periodic. It keeps on repeating after some time. So at what now, after how much time it is repeating, that is what is time period. So time period is having the unit of time, that is seconds. Okay. Then f naught is the fundamental frequency. F naught is actually 1 by T naught, which is known as the fundamental frequency. Fundamental frequency usually having the unit of hertz or cycles per second. That is, my signal is periodic. So periodic means how many cycles are there in 1 second. Okay. So that is also called as hertz. Now one more parameter is omega naught, which is actually 2 pi f naught. Okay. 2 pi f naught is equal to omega naught. That is, f naught is actually number of cycles per second. So cycles per second into 2 pi. 2 pi is the number of radians per one cycle. So how many radians angle is changing for 1 second. Okay, that is what is known as radian frequency. Radian frequency or angular frequency. Angular frequency, so which is having the unit of radians per second. Radians per second. Okay. Now in the sinusoidal function, these are the different parameters. So in the complex exponential also we have a and omega naught, which are already there in the sinusoidal function. There is one more important parameter, sigma naught, which is known as the damping rate. We will see later why do we call it as a damping rate. Damping means the amplitude of the function is decreasing exponentially. Okay. So at what rate the amplitude is decreasing depends upon the value of sigma naught. That is why you call it as a damping rate. Now we'll see some examples for sinusoid functions and complex exponential functions. Okay, and we'll try to draw these functions. So the examples for, first of all, I will write examples for sinusoidal function. Okay, sinusoidal function. The first example is, let us say my g of t is equal to minus 4 sine 200 pi t. For example, I am taking minus 4 sine 200 pi t. The unit is microamperes. So what does that mean? My signal, which is represented as a function, is a current signal. Okay. So that is why it is having the unit of microamperes. Okay. So how do we draw this? That is, I have a sinusoidal function. Okay, so this is my g of t, which is equal to minus 4 sine 200 pi t. So minus 4 means the amplitude varies between plus 4 and minus 4. Plus 4 and minus 4 are the extremities, and at t is equal to 0, it is 0, and the signal is changing in this manner. Okay, this is how the sinusoidal function is changing. Okay, this is 0. Now what is the sinusoidal function means? It should have some time period. So how do you determine the time period? So here in place of omega naught I have 200 pi. So here my omega naught is equal to 200 pi. What is omega naught actually? 2 pi f naught. Okay. 2 by f naught is equal to 200 pi, or what is f naught is 100 or 100 Hz. So if I calculate T naught, which is equal to 1 by f naught, which is 0.01 second, or I can, if I multiply it with 1000, 10 milliseconds. Okay, so that is what is the time period. So starting from here, if I take this, and this is my one complete cycle. So at this point, what is the time? 10 milliseconds. Okay, this is what is the first example for sinusoidal function. Okay, let us try to draw another sinusoidal function. Let us say g of t is equal to 10 cos 10 power 6 pi t nanocoulombs. Coulombs is the unit for capacitance. So how capacitance is changing, okay, with respect to time. So the unit is nanocoulombs. Now let us try to draw this. Okay, so this is my time axis. This is g of t given by 10 cos 10 power 6 pi t. That is 10 into means the amplitude varies between plus 10 and minus 10. So this is these are my extremities. Okay, so cos means that t is equal to 0, cos 0 is 1. So the signal is changing. 1 into 10 is 10. So the amplitude is 10 at t is equal to 0. Then it keeps on changing in this manner. Okay, so this is what is a 10 cos 10 power 6 pi t. Okay, now what is the time period of this? So 10 power 6 pi. So my omega naught is 10 power 6 pi, or f naught is 2 pi f naught is 10 power 6 pi, or 2 pi f naught is 10 power 6 pi. Pi gets cancelled. So what is my f naught now? What is my f naught? 10 power 6 by 2 Hz. Okay, or what is the time period? T naught 1 by f naught, which is 2 by 10 power 6, which is 2 microseconds. Okay, am I correct? So 2 by 10 power 6. 10 power 6 is, if it is going to numerator, 10 power minus 6, 2 microseconds. Okay, this time period at t is equal to 0. This is my starting time. This is one cycle. Okay, from this peak to this peak is one cycle. So what is the time at this point? 2 microseconds. So this is the example for a sinusoidal function. Okay, now we'll see some examples for exponential functions also. So the first example which I am going to give is g of t is equal to 2 into e power minus 10t meters. Okay, that is, the signal here is a distance. So that is why I am giving the unit as meters. So the distance is changing exponentially. So the expression or the function is 2 into e power minus 10t. So let us try to draw this function. Okay, so this is my g of t changing as a function of time. So what is its amplitude at t is equal to 0? 2 into e power minus 10 into 0. E power 0 is 1. Anything to the power of 0 is 1. So 2 into 1 is 2. So it's at t is equal to 0, it is 2. At t is equal to infinity, it is e power minus 10 into infinity, or 1 by e power infinity, or 1 by infinity, which is 0. So it approaches, it is decreasing exponentially, and it is approaching 0 at t is equal to infinity. So this is what is my exponential function. Okay, this is what is my exponential function. Now if I draw a tangent at t is equal to 0, so it is cutting my time axis at 0.1 second. Okay, the slope of the straight line, if I draw a straight line at t is equal to 0, or if I draw a tangent to this exponential function at t is equal to 0, it is going to cut my time axis at 0.1 second. We can determine it. So how do we determine? We have to determine the equation for this. How do you determine the equation for this? You should know it's a slope. How do you find the slope? That is d by taking its derivative. dg of t by dt is equal to 2 into, what is the derivative of e power minus 10t? So 10 into e power minus 10t, okay, so which is equal to minus 20 e power minus 10t. So I am drawing a tangent at t is equal to 0. So what is my dg of t by dt or g dash of t at t is equal to 0 is minus 20 into e power minus 0, which is equal to minus 20. So what is the slope? Minus 20. And at t is equal to 0, what is its amplitude? 2. So what is the equation for this straight line? 2 minus 20t, isn't it? So at t is equal to 0.1, 20 into 0.1 is 2. So 2 minus t is equal to 0. So the amplitude of this straight line is becoming 0 at t is equal to 0.1 second. So that is how we got this time axis intercept as 0.1 second. Okay. So this is the one exponential function. So let us try to take one more example, that is the second example, which is g of t is equal to 5 into e power minus t sine 2 pi t meters per second square. So that is my acceleration. Meters per second square is the unit of acceleration. So my signal is acceleration, which I am representing with a function. Here, actually, if you observe this example, it is a product of two functions, sinusoidal and exponential function. So this sinusoidal function maximum amplitude is 5 and its amplitude is decreasing exponentially. So my amplitude of the sinusoid is 5 into e power minus t. Okay, so if I try to draw this sinusoidal function, then if I try to draw this function g of t, it actually is having a maximum amplitude of 5, and from 5 the amplitude is slowly decreasing. Okay, and how it is decreasing? Decreasing exponentially. Okay, so if I join all these peaks here, then the equation of this dashed line, which is exponential, is actually 5 into e power minus t. So it is called as damping. The amplitude of the sinusoidal signal is slowly decreasing exponentially. So that is why it is called as this minus 1, e power minus 1 into t. So what is my damping rate? What is my damping rate? Damping rate is minus 1. We have seen that in the previous expression, that is minus sigma naught. Sigma naught is called as the damping rate. What is my sigma naught here? It is minus 1. Okay, so the amplitude of the sinusoidal is decreasing exponentially. Okay, it is actually a product of exponential as well as sinusoidal functions. So these are the two important continuous time functions which are used for analysis of signals and systems.